calculated. I'm not going to bother you with that whole gigantic monstrosity thing. But the biggest thing is that objects with a higher diameter, such as hailstones or very large raindrops, return a lot more power, or reflect a lot more power of the radar beam than the smaller raindrops. So up on this diagram here, both of these cubes would return the same reflectivity value, whether it be the left side with just a couple large hailstones, or the right side with many small raindrops and a couple medium-sized raindrops. They would both return the same reflectivity value, which is what we observe on when we look at a weather radar output. So after all that process happens and all the processing occurs, we get a radar image such as this one, which is, I forget exactly which tornado it is, but one of the ones near Moore, Oklahoma at some point, or more, they always seem to be hit. But this depicts a typical supercell there that's moving probably towards the east in that direction. But this is the output of all we just talked about that goes into creating a radar image. And along with this, there are various abnormalities that can appear on weather radar output that are not proper. Because, for example, we'll try and draw this up here a little bit. Let's say that here we have a radar dish, and you have the antenna. And then over here, we can say is a big hailstone. So, for example, what can happen here is the radar beam, it gets transmitted over, and it moves over and it hits the hailstone there. And at this point, as we saw from the previous diagram, the hailstone would then re-emit and scatter all the radiation in various directions. Some goes up, left, right, but some of it can go down toward the surface where it hits the ground. Then from there, the ground can re-emit it back up to where it hits the hailstone again, and then it can re-emit it all the way back to the radar. And this fancy process of from radar to hailstone to ground to hailstone to radar is termed a reflectivity flare or a three-body scatter spike because it hits three different things. And that can create the spike extending off of a storm as seen on the above this little storm depicted on radar. So this spike is not actually, there's no rain falling in this area. It's the result of all the hail in the heavy precipitation region down here that causes this process to happen, and this creates the abnormality there on the radar output. And also what can happen is ground clutter is a major problem in radar. For example, the Lubbock radar consistently hits ground clutter northeast of town, and is depicted on this radar image as this mass of abnormally bright colors, and if I were to play this, would stay fairly constant. And that's because the radar beam, for whatever reason on these days, gets tilted downward back toward the ground, hits per se a windmill or giant grain silo, could be anything, and then that re-emits some of the pulse back towards the radar dish, and it gets picked up back there as a output that is not really there, or not hydrometeor, I should say. Next, I'm going to briefly introduce the concept of Doppler velocity, as radars can not only provide images of the intensity and extent of hydrometers in the atmosphere, but they also provide information on their movement, whether it be towards or away from the radar. And to start with this, I have to introduce a concept of this general Doppler velocity. And I'm sure you've all probably seen or heard the example of when there's an emergency vehicle coming toward you, how the tone of their siren gets higher pitched and louder as it's approaching you. But then as it passes you and heads in the other direction and you're behind it, the tone gets a lower and lower frequency and becomes much quieter. And that is because of the Doppler shift or Doppler velocity phenomenon. This is a very useful graphic of how it works for hydrometeors. As just like if the ambulance is coming towards you, which is, for say, here on the bottom case, if the raindrops or hailstones, whatever, are moving towards the radar, the backscatter emitted by the raindrops or hailstones back to the radar after it gets hit by that initial radar beam has a higher frequency than the original EM wave that the radar emitted in the first place. And the radar, through very fancy technology, which is on the scope of an upper level grad course, the radar measures that change in frequency, and if the returned frequency from the hydrometeors is higher than the frequency that the radar emitted, it knows that the hydrometeors, the raindrops, are headed towards the radar. Conversely, as shown on the top example, if the raindrops or whatever are heading away from the radar, then the radiation returned to the radar dish by the raindrops carries a lower frequency than the initial radar pulse. And again, the radar calculates how extreme the difference is, and from there it can conclude how quickly the raindrop or hailstone is moving away from the radar. And this is an image of radar velocity. So key thing here is the green and blue colors denote wind that is blowing towards the radar, whereas the red depicts winds blowing away from the radar. And I believe this is an example of a storm coming through. So if I were to draw arrows on here depicting the wind direction, so say we have the red in the middle and then the greens there to the right of the radar, and the radar is at this black circle here, which is the Lubbock radar right by the Lubbock airport. So if I were to draw wind vectors, just a couple on here to get the point across. So they can be going towards the radar and then away from the radar. Again, be going towards and away. Same thing, towards and away. And then again down here, same thing, towards and away. However, on the left side of the outbound velocity region here shown in red, on the left side, those winds are going towards the radar, going from west to east in that westerly direction. So if I draw that on there too, draw those wind vectors, you see that we have the converging winds there west of the Lubbock Loop, and this can help to tell us that there is either a front, or in this case, just a strong storm that has strong winds associated with it, that is overpowering and overtaking the base environmental winds. And if you're anywhere in the region, say underneath or ahead of the strong bluish colors which denote very strong wind speeds, probably should have a severe storm warning, which is issued here in this case, shown by the yellow polygons, and depicts a strong windstorm is heading in towards Lubbock. And a couple other fun things that radars can do is, so for example, I'm going to draw one more case on up here. So, really briefly, I want to introduce the concept of the correlation coefficient. Marker's not doing so well, but like some person. So, correlation coefficient, what the radar can measure is the radar can send out pulses that are, but the radar emits radiation, or emits pulses that are both, say, up and down, so it travels in this pattern, or it's hard to draw this other case on here, but imagine you emit pulses that have wave crest and trough traveling in this direction, but also in the horizontal direction as well. And what that allows you to do is if you have a base raindrop here, let's say you'll get even return from this dimension and even return from this dimension. So a small raindrop has a correlation coefficient that is very boring. It would be 0 or 1 in that case. However, if you get, say, a giant 2x4 in a tornado of a house that gets destroyed, the dimensions of the returns radiation will be much greater in the vertical extent than in the horizontal extent. And the radar compares the return of the vertical versus horizontal return. And if they're nowhere near similar, then it can tell that it is probably not a meteorological phenomenon that is measuring the atmosphere, and thus it denotes it as a low correlation coefficient, and it gives a blue coloring around that region. As if you're a weather radar guru or fanatic, you may know that the top left reflectivity plot on there denotes a supercell hook. This is where a tornado could possibly be. If you're enrolled in the ATMO 1100 lab, we'll talk more about this in lab 8 later on in the semester. Then you have the reflectivity image there on the right, which denotes a circulating wind pattern. And then all that goes to the bottom left, where it has that circle of blue or low correlation coefficient values, and combine the hook, the time rotation couplet, and the low CC value. There's a very good chance that there would be a tornado at that location at that time. And it'd probably be rather significant as it is picking up a lot of non-meteorological objects, as given the blue color there on CC. And really briefly, I'm just gonna skip the video for time purposes, but the new era of weather radar is going to be probably called, or it's called phased array radar. And instead of having a dish that travels in circles, goes up in elevation, goes in more circles, instead of that, it'll be more of a flat sheet with a bunch of radar transmitters that can be pointed in any direction of interest. So, for example, I think I'm just going to pull up a stopped point in the video here real quick. For example, what it can do is say that there's a tornado there on the right side of the screen. What the forecasters will be able to do is point the radar directly at the tornadic region of the storm and get the most up-to-date information on the storm itself. Because with the tornado there, you have no purpose really to go around and around again, and all we really hear about is the main tornadic circulation. So, fun thing is, again, we're still using 1988 radars, so when this will actually come into effect and be implemented, phased array radar, who knows? You know as well as I do. They're hoping early 2030s, but again, you never know with that and how this all works. So with that being said, I'm going to get into a little bit of pretty picture time, which I'm sure will probably be a bit more fun for all of you in the base radar fundamentals. So we have a very thin line of storms, which has many names. It's called a squall line, could be just a general line of storms. But for example, you just have that thin line up and along a cold front per se. You'll get a long thin band of heavy rainfall and associated with the front. And then when that passes, then you're essentially dry again and in the much cooler air mass. This is when I was back in Nashville over the summer there, have that thin line of storms move on through. And, of course, radars do not only pick up hydrometeors, of course, they can pick up the smaller scale features, such as dust that gets lifted up when a front is coming through. For example, this is back in the fall sometime, but as you can see, it's this thin little band of elevated reflectivity values, and that is just either dust, insects, or whatever being measured by the radar as the front passes on through it, lifts them all up into the sky. So if you ever look at radar, see a thin little boundary such as this is probably a weak front or something that's coming through, and this will probably get wind speed shifts and either cooler or warmer air moving into your region. Sometimes you get a mix of, say, those little frontal boundaries or outflow boundaries and also rain. This is another case from the fall where you see all the green, yellow, and orange colors denoting rainfall. Green on here shows like light precipitation, light rain, whereas the orange shows heavy rain. And you'll see that giant just cluster of rain there west of Lubbock. And you also see, as the rain falls down to the ground, as it hits the ground, it kicks up a bunch of dust, which can cause a little mini cold front to form out ahead of the line of storms. And that is observed, maybe black is the best color to do, it shows up better on there. But that little boundary from Moleshoe down to Bledsoe, forgive my pronunciations if they're not proper. And that little boundary is a pocket of cooler air that is being pushed out ahead by the rainfall back to its west. And these can sometimes appear as shelf clouds, could just be non-observable to the naked eye. Could be a bunch of different things that you would see as that little boundary would pass over your location. And this was another case back in the fall. If I remember correctly, this was the day where you had the dust storm back in October, November, I forget exactly. But you had the heavy rains off to our west, shown in the orange colors there on the radar reflectivity. And it's not really formed yet, but you can see the makings kind of a outflow boundary from the storms pushing outward with that cooler air, with the radar picking up the dust as the dust storm was beginning. Then later on, as it moved in towards Lubbock, we got this wonderful day of strong, swirly dust there in that October or November of last semester. And this is a recent addition this morning, this talk, as we had the dust storm yesterday and all those strong winds combined with low humidity, low moisture in the region up north of us, created fires in the Oklahoma Panhandle. And in fact, you'll see these little swaths of reflectivity all emanating from one point, kind of. And I'm not sure what the video was. Maybe. No, all right. But if you were to watch, all of these little plumes of reflectivity would be emanating from one single point on the southwest side of the plume. And those colors you see on there, those greens and yellows, are actually, they are smoke from the fires that are going on in the Oklahoma Panhandle. And those are just all the smoke plumes being blown off up to the northeast. And these are fairly strong smoke plumes. I haven't seen really many this strong in a very long time. Just shows the extent of the fire danger that there was yesterday, as well as how primed the land was in that area for the wildfires to begin. And also that, but this is the case from one of the research projects that we're doing. And so this is a more in-depth radar topic, I'll say. But this is a supercell from northwest of Lubbock back in the 2000s. And supercells They are a rotating storm, as you'll learn more in the lab, or lab 8, further on in the semester if you're in the labs. But they create winds that are blown around the storm in the counterclockwise fashion. And looking at the reflectivity image there on the right, it's very grainy on the right-hand side, but you have winds, the environmental winds that are blowing from, let me different color on here. Environmental winds blowing from east to west. And then with the storm outflow, or the fancy term is rear flank downdraft, you see the winds blowing towards the our tower and our research site. So this is not a very clear example. It's applicable to our research. We'll go ahead and move on from this. This is the case from the fall when we had a supercell, a left-moving supercell, all the fancy terms they introduced here. As again, we see a kind of backwards hook on the reflectivity image on the top right. You see the radar couplet. And there was no tornado from the storm, so there was no CC, correlational image to see. But if you match up the top with the radar image, with the reflectivity image, you have some pinks in there which denote hail. And then you have the couplet, the rotation couplets on the beneath that. So again, similar case there, you use the radar to see rotation in the storm. Now this one I'm sure rings a lot of bells for all of you. As back at the first football game last year, we had this giant shelf cloud move over the football stadium before we got that heavy downpour on that day. And someone did report a funnel cloud on this, but I don't think that ever happened. But anyway, there was a outflow boundary that you can highlight as the rain-cooled air from the storm hits the surface, blows outward in all directions, and it produces a mini cold front ahead of it. It's circled there in blue. And as that mini cold front got closer to Lubbock, it produced that giant mothership-looking cloud structure, beautifully striated. It's created that beautiful shelf cloud, and you'll notice that when that shelf cloud moved overhead, the rain didn't start initially. It started a couple minutes later, and that becomes clear why when you look at the radar image, because the circled boundary, which denotes the leading edge of the scary looking cloud there on the right, is not where the precipitation begins. The precip in this case is all the way back by New Deal, when the front of this cloud was approaching the Lubbock Airport radar there. This is another fun case of, when I was in Amarillo recently, had a supercell on with a bunch of hail and lightning there in that supercell. I think it was warned for baseball-sized hail, if I remember correctly. And the right-hand side there shows my view from the hotel room as the storm was approaching us. Similarly, radar images also on the left-hand side, a small little cell of rain. This is a photo taken from a research project that Dr. Khalid's group did back in the summer. As he had this little, just monsoon, small cell of rain there over the New Mexico desert. And on radar, it just showed up as a little blip of intense, heavy rain, which is, to kind of put it into perspective, a small little blip on radar looks like that in the real world there on the right-hand side. Another case here of a supercell back in southwest Kansas. As again, we have that hook echo feature there. There was a wall cloud reported on this and later a funnel cloud. But all I really saw was the rain as a pretty picture there on the right-hand side there of the screen. And just one more little fun case down in Oklahoma. You can see the beautiful updraft from the supercell that's shown by this column of rapidly rising air, and then the rain would be on the north side of the system as the tall column of air I'm looking at tall traffic looking at here would be in about this region, whereas all the rain would be falling up to the north of it. That's why we can see the beautiful cloud structure here with no rain obstructing our view there from that. There's more pictures of how that's progressed there throughout the day. And if you follow Reed Timriddle, popular storm chaser, yes, I saw the Dominator on this day there in Southwest Kansas. Then, see here, second to last pretty picture here. This was in southeast Missouri back in May. As again, there is a little tornadic hook on there, and a hail core, also shown by the pink colors. There's a little bit of rotation, probably a bit too close to where I was on that day for comfort. Denoted there in the blue circle. However, yeah. And then on the right-hand side, you see the picture the storm produced. It was largely not really tornadic in the end. See, it did have a tornado warning on it, but it did produce this beautiful, thin-looking shelf cloud there on the right-hand side of the screen. So a common misconception is that shelf clouds mean that there's a tornado coming sometimes. No. Shelf cloud just indicates there's probably strong winds as associated with the storm, but it's not inherently a strong tornado per se. See a shelf cloud when it passes overhead, have a couple minutes to get inside before all the strong winds and rain really impacts you. Then one final image here. Sometimes when you're just looking at radar, it's fun to see what poor storm chasers are caught in the middle of the hail core, such as Tim Marshall here back in May. Popular storm chaser and really esteemed researcher, but probably needed a new windshield after this one.